paralleling two different types of conductors, such as a 1/0 conductor and a tape shield, on a 12.7 kilovolt primary circuit is not permissible. The fundamental reason is that different conductors possess varying current carrying capacities and impedances. When conductors with unequal capacities are paralleled, it can result in an uneven distribution of current. This uneven distribution can lead to overheating and potentially to failures within the electrical system. The tape shield is not designed to carry return neutral current. Its primary function is to provide shielding against electrostatic stress and lightning surges. Using the tape shield to carry return neutral current can compromise the insulation and elevate the risk of ground faults. If the tape shield is inadvertently used to carry return neutral current, the tape shield termination will be subjected to undue stress. This stress can manifest as overheating and eventual damage. In conclusion, paralleling 1/0 conductors with the tape shield on a 12.7 kilovolt primary circuit is not an acceptable practice. The tape shield should only be used for its intended purpose, which is shielding and not for carrying return neutral current. To elaborate further, it's crucial to understand the distinct roles and limitations of each component in a high-voltage system. Firstly, the 1/0 conductor is typically sized to handle a specific load current based on ampacity tables and voltage drop calculations. Its design and material composition are optimized for carrying current efficiently and safely within defined temperature limits. Secondly, the tape shield, on the other hand, is a thin metallic layer wrapped around the cable insulation. Its primary function is to provide an equipotential surface that helps to contain the electric field within the cable and to protect the cable and surrounding equipment from electromagnetic interference. The shielding is particularly important in high-voltage applications where the electric fields can be intense and can induce unwanted currents in nearby objects. Thirdly, paralleling conductors is a technique used to increase the current carrying capacity of a circuit. This is typically done when a single conductor of the required size is either unavailable, impractical to install, or too costly. The NEC National Electrical Code provides guidelines for paralleling conductors, stipulating that they must be of the same material, same size, same insulation type, and terminated in the same manner. The code aims to ensure that the current is evenly distributed among the parallel conductors, preventing any one conductor from being overloaded. Now, let's consider what happens when you attempt to parallel a 1/0 conductor with a tape shield. The 1/0 conductor is designed to carry the main load current, while the tape shield is not designed to carry any significant continuous current. The tape shield is typically grounded to provide a path for fault current in the event of an insulation failure, but it is not intended to serve as a parallel current carrying conductor. If you force the tape shield to carry a portion of the load current, several problems can arise. 1. Uneven current distribution. The 1/0 conductor and the tape shield have vastly different impedances. Impedance is the total opposition to current flow in an alternating current circuit, and it includes resistance and reactance. The 1/0 conductor has a relatively low impedance, while the tape shield has a much higher impedance due to a small cross-sectional area and the material it is made of. This difference in impedance means that the 1/0 conductor will carry the vast majority of the load current, while the tape shield will carry only a small fraction. However, even a small amount of current flowing through the tape shield can cause it to overheat. 2. Overheating. The tape shield is not designed to dissipate heat effectively. It is typically thin and wrapped tightly around the cable insulation, which acts as a thermal insulator. Any current flowing through the tape shield will generate heat, and this heat will be trapped within the cable. This can lead to a localized hotspot, which can degrade the insulation and eventually cause a failure. 3. Insulation damage. The insulation surrounding the tape shield is designed to withstand high voltage stress, but it is not designed to withstand high temperatures. Overheating of the tape shield can cause the insulation to break down, reducing its dielectric strength and increasing the risk of a flashover or ground fault. 4. Ground fault risk. If the tape shield overheats and damages the insulation, it can create a path for current to flow to ground. This can result in a ground fault, which can trip a circuit breaker or cause other protective devices to operate. A ground fault can also pose a safety hazard to personnel who may come into contact with the faulted equipment. 5. Termination stress. The terminations of the tape shield are typically designed to provide a low impedance connection to ground. However, if the tape shield is carrying a significant amount of current, the terminations can become overloaded and overheat. This can lead to a loss of the ground connection, which can compromise the shielding effectiveness of the tape shield and increase the risk of electromagnetic interference. The NEC is very specific about the requirements for paralleling conductors to ensure safety and reliability. These requirements are in place to prevent the problems. According to the NEC, conductors must be of the same material, for example, copper or aluminum, to ensure that they have similar conductivity. They must be the same size, meaning the same cross-sectional area, to ensure that they have the same ampacity. They must have the same insulation type to ensure that they have the same temperature rating. They must be terminated in the same manner to ensure that the current is evenly distributed among them. These requirements are intended to prevent uneven current distribution, overheating, and other problems. In a specific scenario described, where the utility suggests paralleling a 1/0 conductor with a tape shield, it is important to understand that this does not meet the NEC requirements for paralleling conductors. The tape shield is not a conductor in the conventional sense, and it is not designed to carry load current. It is a shielding component that is intended to be grounded. Attempting to use the tape shield as a parallel conductor can create a dangerous situation and should be avoided. It is essential to consult with a qualified electrical engineer and to follow all applicable codes and standards to ensure the safety and reliability of the electrical system. If additional current carrying capacity is needed, the correct approach is to install appropriately sized conductors that meet the NEC requirements for paralleling. In summary, firstly, do not parallel different conductor types. Secondly, tape shields are not intended for current carrying. Thirdly, improper use stresses the shield and termination. Fourthly, always adhere to NEC guidelines. Always prioritize safety and consult with qualified professionals. For instance, consider a scenario where a 1/0 copper conductor is paralleled with the tape shield on a 12.7 kilovolt primary circuit. The 1/0 copper conductor has an ampacity of approximately 150 amps, depending on the insulation type and installation conditions, as per NEC Table 310.15. The tape shield, on the other hand, is not designed to carry any significant continuous current. Let's assume that the load in the circuit is 100 amps. If the 1/0 conductor and the tape shield were perfectly paralleled and the current was evenly distributed, each would carry 50 amps. However, due to the difference in impedance, the 1/0 conductor will carry the vast majority of the current, say 95 amps, while the tape shield will carry only 5 amps. Even though 5 amps may seem like a small amount of current, it can be enough to cause the tape shield to overheat, especially if it is not properly grounded or if the terminations are not properly made. The heat generated by the current flowing through the tape shield can degrade the insulation, leading to a ground fault or a flashover. In addition, the terminations of the tape shield may not be designed to carry even 5 amps of continuous current. The terminations can overheat, causing the connection to become loose or corroded. This can further increase the impedance of the tape shield, leading to even more heat generation and a higher risk of failure. To illustrate the potential consequences, imagine that the tape shield is carrying 5 amps of current, and its resistance is 0.1 ohms. The power dissipated as heat in the tape shield would be calculated as follows: power equals current squared times resistance, which is 5 amps squared times 0.1 ohms equals 2.5 watts. While 2.5 watts may not seem like a lot of power, it is concentrated in a small area, and it can be enough to raise the temperature of the tape shield and the surrounding insulation significantly. Over time, this can lead to a breakdown of the insulation and a failure of the cable. Furthermore, consider the voltage drop across the tape shield. With a current of 5 amps and a resistance of 0.1 ohms, the voltage drop would be voltage equals current times resistance, which is 5 amps times 0.1 ohms equals 0.5 volts. This voltage drop may not seem significant, but it can create a potential difference between the tape shield and the grounded enclosure, which can increase the risk of a ground fault. In a properly designed and installed high-voltage system, the tape shield is grounded at multiple points to minimize the voltage drop and to provide a low impedance path for fault current. However, if the tape shield is carrying load current, the voltage drop can become significant, and the grounding system may not be able to effectively mitigate the risk of a ground fault. Therefore, it is essential to avoid using the tape shield as a parallel conductor and to ensure that it is properly grounded and used only for its intended purpose of shielding. If additional current carrying capacity is needed, the correct approach is to install appropriately sized conductors that meet the NEC requirements for paralleling. This will ensure the safety and reliability of the electrical system. The NEC specifies that paralleled conductors must be of the same material, same size, same insulation type, and terminated in the same manner. This is to ensure that the current is evenly distributed among the paralleled conductors and that no one conductor is overloaded. It is also important to consider the voltage rating of the conductors in the insulation. In a 12.7 kilovolt primary circuit, the conductors must be rated for at least 15 kilovolts to provide adequate insulation and to prevent flashovers. The insulation must also be suitable for the operating temperature and environmental conditions. The tape shield, on the other hand, is typically not rated for high voltage or high temperature operation. It is a thin metallic layer that is designed to provide shielding, not to carry load current. Therefore, it is not appropriate to use the tape shield as a parallel conductor in a 12.7 kilovolt primary circuit. In addition to the electrical considerations, there are also mechanical considerations to take into account. The 1/0 conductor is typically a stranded copper or aluminum conductor that is designed to withstand the mechanical stresses of installation and operation. The tape shield, on the other hand, is a thin metallic layer that is easily damaged. If the tape shield is used as a parallel conductor, it may be subjected to mechanical stresses that it is not designed to withstand, leading to a failure of the cable. Therefore, it is essential to follow all applicable codes and standards and to consult with a qualified electrical engineer to ensure the safety and reliability of the electrical system. In the scenario presented, the utility's suggestion to parallel a 1/0 conductor with the tape shield is not in accordance with good engineering practice or the requirements of the NEC. It is important to push back on this suggestion and to insist on a safe and compliant solution. If additional current carrying capacity is needed, the correct approach is to install appropriately sized conductors that meet the NEC requirements for paralleling. This will ensure the safety and reliability of the electrical system and protect personnel from electrical hazards. For a 12.7 kilovolt primary circuit, the conductors should be sized based on the load current, the voltage drop, and the ampacity of the conductors. The conductors should also be protected by overcurrent devices such as fuses or circuit breakers to prevent overloading and short circuits. The overcurrent devices should be sized according to the NEC requirements and coordinated to ensure selective tripping. In addition, the grounding system should be properly designed and installed to provide a low impedance path for fault current and to protect personnel from electric shock. The grounding system should be tested regularly to ensure that it is functioning properly. The tape shield should be grounded at multiple points to minimize the voltage drop and to provide a low impedance path for fault current. The grounding conductors should be sized according to the NEC requirements and connected to a grounding electrode system that meets the NEC requirements. In summary, the use of tape shield as a parallel conductor on a 12.7 kilovolt primary circuit is not a recommended or safe practice due to the differences in impedance, current carrying capacity, and the intended function of the tape shield. Always adhere to established electrical codes and engineering practices to ensure the safety and reliability of electrical systems. The correct approach is to use appropriately sized conductors that meet the NEC requirements for paralleling, which will ensure the safe and reliable operation of the electrical system and protect personnel from electrical hazards. Furthermore, consider the long-term effects of such a setup. Even if the tape shield initially seems to handle a small amount of current, the cumulative effect of heat cycles, corrosion, and mechanical stress can lead to a gradual degradation of the shield and its terminations. This degradation can eventually result in a complete failure of the shield, compromising the safety and reliability of the entire system. The cost of repairing or replacing a damaged cable in a 12.7 kilovolt primary circuit can be significant, both in terms of materials and labor, as well as the potential downtime and disruption to service. Therefore, it is essential to avoid any practices that could potentially damage the cable or reduce its lifespan. In addition to the technical considerations, there are also legal and liability issues to consider. If an accident or injury occurs as a result of improper electrical work, the responsible parties can be held liable for damages. This can include the electrician, the contractor, the utility, and even the property owner. Therefore, it is essential to ensure that all electrical work is performed in accordance with applicable codes and standards and that all personnel are properly trained and qualified. In the case of the 12.7 kilovolt primary circuit, it is particularly important to exercise caution and to seek expert advice. High voltage systems can be extremely dangerous, and even a small mistake can have serious consequences. Therefore, it is essential to follow all safety procedures and to use appropriate personal protective equipment when working on or near high voltage equipment. This includes wearing insulated gloves, safety glasses, and other protective gear as required. It is also important to de-energize and ground the circuit before working on it and to verify that the circuit is de-energized using a voltage tester. In conclusion, the practice of paralleling a 1/0 conductor with a tape shield on a 12.7 kilovolt primary circuit is not a safe or recommended practice. It violates established electrical codes and engineering practices and can lead to serious consequences, including equipment damage, personal injury, and legal liability. Therefore, it is essential to avoid this practice and to follow all applicable codes and standards to ensure the safety and reliability of electrical systems.